Welcome back to the channel. Today, we explore a fascinating idea: why natural language processing, or NLP, can be thought of as quantum in nature, and how quantum-inspired frameworks are reshaping the way machines understand language. When we examine language closely, we realize something profound: meaning isn't stored in isolated words. Instead, it emerges from how words interact, combine, and influence each other. This is exactly why many researchers say NLP mirrors quantum behavior. In quantum mechanics, you've probably heard terms like superposition and entanglement. They describe how particles can hold multiple states at once or become deeply interconnected. Surprisingly, language behaves the same way. A single word can carry multiple meanings depending on context. That's like linguistic superposition. And when words combine, their meanings intertwine and shape each other, almost like semantic entanglement. This is where the compositional categorical framework becomes so powerful. It gives us a mathematical way to combine meanings in a structure similar to quantum processes. And within this framework, we have something called distributional compositional categorical grammar, or discopy, which blends grammar rules with vector-based meaning representations. Put together, these ideas allow NLP models to capture deeper, more human-like semantic understanding far beyond traditional text processing. This whole approach has deep roots in lambeq's pre-group grammar, which helps us understand how words combine to form valid sentences. Think about it: we don't memorize every sentence in the world. We only know words and how they behave. If we understand each word's grammatical type and meaning, we can combine them to create or interpret an infinite number of sentences. Quantum natural language processing, or QNLP, builds directly on this idea. It merges linguistic structure with meaning using concepts adapted from quantum computing. In QNLP, the meaning of a sentence is formed the same way quantum states combine, through structured, rule-guided interactions. And the result? A modeling approach that captures language more efficiently, more naturally, and far more richly, closer to how humans actually understand each other. What this framework really gives us is a unified mathematical model, a way to bring together two powerful ideas. First, the distributional theory of meaning, where words are represented as vectors based on how they appear in context, and second, a compositional theory of grammar, which explains how words fit together structurally. So essentially, we are merging vector space semantics with grammatical types into one elegant quantum-inspired system. Think about our classical vector space models. Nowadays, whenever we process language, we convert every single word into a vector. That gives us representations like the vector for king, the vector for queen, man, woman, and so on. And with basic vector algebra, we can compute relationships like king minus man plus woman is equal to queen. But here's the catch: this approach only uses distributional meaning. It doesn't incorporate grammatical structure. In a quantum-inspired framework, we go a step further. We don't just represent words as vectors, we also combine their grammatical structures using pre-group grammar. We weave both meaning and syntax together using principles borrowed from categorical quantum mechanics, CQM. And this is where ZX calculus comes in. ZX calculus allows us to convert these quantum-like linguistic processes into actual quantum circuits. So in our demonstration, we'll take a sentence, turn it into a string diagram, simplify that using cup and cap notation, and then transform it into a quantum circuit that can run on a simulator or real quantum hardware. And I'll walk you through that step by step. Now, a natural question arises: why do we even need quantum NLP when classical NLP is already so advanced? Well, classical models still struggle with some fundamental limitations. Ambiguity, context sensitivity, polysemy, words like bank, apple, light, train that change meaning depending on context. In classical NLP, disambiguation is done using fixed-length vectors. But this approach hits a wall. Quantum NLP, on the other hand, uses superposition, allowing a word to hold multiple meanings at once and collapse to the correct meaning when context is applied. This makes disambiguation faster and more natural. Then there's computational complexity. Transformer models need massive data, huge corpora, enormous compute power. Quantum models, however, leverage quantum parallelism, allowing complex computations like parsing and feature selection to happen more efficiently. Another major challenge in NLP is long-distance dependencies. Even with transformers, we still need positional encoding to tell the model how far words are from each other. But in quantum systems, entanglement naturally links distant parts of a sentence, preserving both syntax and semantics effortlessly. Take the word bank. It may refer to the side of a river, a financial institution, or something else entirely depending on context. Quantum NLP lets us represent the word as a superposition of all its possible meanings and then collapse it to the correct meaning when we see the sentence around it. Now consider the sentence, "The book that John read yesterday was interesting." Here, book and interesting are tightly connected. If there's no book, there's nothing to be interesting in the first place. Quantum entanglement models this relationship naturally, linking to distant words so their meaning becomes inseparable. This also works beautifully in long conversations, where classical methods often fail, but quantum structures maintain coherence across large spans of text. Data sparsity. Quantum models reduce it. Search space explosion. Quantum NLP helps shrink and accelerate it. And overall, the entire computation becomes more powerful, more efficient, and more aligned with the underlying structure of human language. Let's take a simple sentence, "Doctor treats patients." Now, in classical NLP, each word is represented using a fixed-length vector. Imagine each word here, doctor, treats, and patients, is represented using a 2000-dimensional vector. So the word doctor maps to a 2000-dimensional space, treats maps to a 2000-dimensional space, and patients also maps to a 2000-dimensional space. These vectors capture how each word relates to all other words in context. Now, if we want to combine the meanings of doctor, treat, and patient using the tensor product, the resulting space becomes enormous. In fact, this combination would require roughly 8 times 10 to the power 9 bits, which is nearly 1 gigabyte of memory just to analyze one sentence. But in quantum NLP, things look very different. A system with n qubits can represent a state in a 2 to the power n-dimensional Hilbert space. This means that the same 8 times 10 to the power 9 bits, about 1 gigabyte, can be represented using just 33 qubits. That's the power of quantum representation. And this is just the beginning. We used a 3-word sentence as an example, but in reality, sentences can get longer while noun dimensions stay the same. Imagine you have 10,000 verbs in your language model, and you want to understand how they relate to nouns. Classically, this could require 80 terabits of memory space. But quantum computation only needs 47 qubits to represent the same information. And it scales even more impressively. 10,000 verbs. 1 million dimensional noun vectors. Classical requirement exabytes of memory. Quantum requirement 73 qubits. This is an astronomical gain in space efficiency, making quantum NLP an incredibly attractive approach for large-scale language modeling. Now let's talk about time complexity, another crucial area where quantum NLP shines. In many NLP tasks, we need to compute the distance or similarity between sentences for paraphrase detection, information retrieval, or finding which document is closest to a query. Classically, if you have a search space of m vectors, each of n dimensions, computing similarity takes order of nm time. For example, let's say you have 1 million training vectors and each vector has 10,000 dimensions. Classically, this becomes a massive 10 to the power 10 operations. But with quantum algorithms, the complexity reduces to order of square root of nm times log m. This gives you almost a 10,000 times speed boost. So quantum NLP doesn't just save memory, it massively accelerates computation. So far, everything we discussed is from a theoretical perspective. Can we implement these ideas right now? Yes, but with limitations. We are currently in the NISQ era, meaning quantum hardware is still noisy and not powerful enough for large-scale deployment. But the good news is, even without full quantum hardware, we can still experiment using quantum simulators. And in the next part, I'll show you exactly how to implement these ideas using a simulator backend step by step. Now let's look at the NLP pipeline we'll be using in our implementation. Whenever we are given a sentence, the first thing we want to do is parse it to understand how the words relate to each other syntactically. For this, we use a special parsing approach called Dependency Compositional Categorical Grammar or DCCG. In our workflow, the parser we'll be using is the Bobcat parser, developed by Quantinuum in collaboration with Cambridge University. This parser takes a natural language sentence and returns a structured representation that we can convert into a very special format, a string diagram. Now, what is a string diagram? A string diagram is an incredibly elegant way to show how words relate to each other as a quantum process. Instead of dealing with huge matrices or complex algebra, a string diagram gives us a clean, visual, abstract representation of meaning composition. For example, take the sentence, "The cat sat on the mat." When we parse this sentence, we can draw a string diagram where the words the and cat become entangled using a cup notation. You will also see symbols like n, n.l, and n.r, which come from pre-group grammar and indicate how grammatical types connect. From this string diagram, we can directly construct a quantum circuit, something we can run on a simulator or a quantum backend. But here's the challenge. Complex sentences create complex string diagrams, and converting them into quantum circuits often leads to huge circuits requiring more qubits. For instance, in the diagram of our example sentence, if you count the wires or strings, you'll find 13 strings corresponding to 10 noun wires and 3 sentence wires. This means the quantum circuit would require a minimum of 13 qubits. That's expensive. So what do? We reduce the number of strings in the diagram using rewrite rules. These rules come from grammar like prepositional rewrite rules, determiner rewrite rules, and more. By applying them, we simplify the diagram, reduce redundancy, and drop the qubit requirement significantly, for example, from 13 qubits down to 7 qubits. Why is this important? Because natural language can be ambiguous. A single sentence can have multiple valid syntax trees even though the meaning is consistent. For example, Ram likes Sita and Sita likes Ram have similar structures, and by normalizing their string diagrams, we can compare them effectively and compute their similarity. So simplification helps in two major ways. Reduces qubit requirement, making circuits feasible. Normalize structure, enabling comparison of semantic similarity. Finally, once we have the optimized string diagram, we can use different kinds of ansatz to convert it into a quantum circuit. One popular choice is the IQP ansatz, but there are several others depending on the structure and complexity. In the implementation part, I'll show you how to perform this conversion step by step and run it on a simulator. So now, let's understand the real essence of the quantum circuit we just built. From the optimized string diagram, we can convert everything into a Qiskit quantum circuit, which is compatible with the IBM Qiskit backend. For example, our sentence, "The cat sat on the mat," gets transformed into a circuit using 7 qubits, and at the bottom, we have classical wires where measurements will be taken. Now, what's really interesting is what's inside this circuit. You will see a variety of quantum gates, Hadamard gates, rotational gates like Rx, Ry, Rz, and even many trainable parameters. These parameters are generated automatically when two Bobcat parsers process your sentence. For instance, you might see a parameter name like cat_n_1. This tells us that cat is a noun, category n, at index 1, and we want to learn the optimal rotational angel assigned to it. During training, the model adjusts these angels so the circuit's final measurement matches the correct label. Let's say we are doing binary sentiment classification, positive versus negative. Every sentence in your dataset will be converted into a corresponding quantum circuit with its own parameterized gates. When we train, we optimize these parameters, these angels, until the circuit correctly classifies sentences as 1, positive, or 0, negative. So these angels are essentially the weights of a quantum neural network. Now let's revisit how we actually convert a string diagram into a real quantum circuit. Earlier we saw an example string diagram with 13 wires, meaning we originally needed 13 qubits. In the diagram, words like the and cat are connected, meaning they are entangled. Similarly, words like sat, on, and mat interact in another substructure. Using ZX calculus rules, we know that a cup-shaped wire represents a Bell state, an entangled state. So if two inputs are connected by a cup, as in the cat or sat on, that corresponds to a Hadamard's gate followed by a CNOT gate. This is how entanglement is represented in a circuit. So, once the string diagram is analyzed, converting it to a circuit becomes straightforward. Apply the ZX rules, insert the Hadamards, insert the CNOTs, and build the full circuit. During implementation, you will often hear about layers. Layers simply mean repeating a certain block of gates multiple times. More layers increase the expressiveness of the circuit, allowing deeper analysis. For example, if we repeat the cat entanglement block multiple times to Hadamards and a CNOT, we are analyzing the relationship more deeply. Just like in classical neural networks, deeper layers allow richer modeling. Layer-wise architecture is very popular in variational quantum circuits, QNN models, quantum optimization algorithms. So increasing layers increases the power of your quantum NLP model as long as you have the computational resources. So ultimately, this is what happens. Given any sentence, we convert it into a quantum circuit. Now imagine a dataset where every sentence is represented as a circuit and every circuit has a label. This becomes a quantum dataset. Now we can apply a hybrid quantum classical algorithm to learn the weights. Here the weights are simply the rotational angels inside the circuit. During training, the quantum machine runs the circuit. A classical optimizer updates the angels. The process repeats until the model converges. Once training is complete, you can input a new sentence, for example, Varun is cheerful. Convert it into a circuit, run it through the quantum processor, and the model will output whether it is positive or negative sentiment. That's the power of quantum NLP. Now that the conceptual foundation is clear, let me show you how we can write the actual code using a tool called lambeq. Now, let's move on to the coding pipeline and understand how we actually turn a natural language sentence into a quantum circuit. To do this, we need a few important Python packages: lambeq, discopy, pytket, and Qiskit. I'm using Google Colab here so that all installations can be done with simple pip install commands. lambeq is the quantum NLP toolkit built by Quantinuum, originally developed at Cambridge University. Its main job is to convert classical sentences into categorical representations following the discopy model, so that later those diagrams can be mapped into quantum circuits for machine learning tasks like sentence similarity, binary classification, or multiclass classification. Discopy, on the other hand, is a compositional category theory-based library for diagrammatic reasoning. It provides the mathematical structure behind these diagrams. Think of discopy as the bridge. It connects linguistic structure with quantum formalism in a clear, graphical way. Next comes pytket, which serves as a link between lambeq's diagrammatic output and IBM's Qiskit ecosystem. Once lambeq generates the diagram and discopy structures it, pytket helps us build a Qiskit-compatible quantum circuit that we can run on simulators or IBM quantum backends. So the overall pipeline is simple. Sentence arrow tokenization arrow parse tree arrow string diagram arrow quantum circuit. We begin with tokenization using lambeq's SPSA tokenizer. Tokenization is extremely important because sentences often contain dots, abbreviations, and special characters that naive splitting methods cannot handle. For example, Professor P.K. Roy is visiting I.T today. If you split only by dot, you'll get completely wrong tokens. Using SPSA tokenizer, however, gives you the correct tokens like Professor, PK, and IIT, so tokenization ensures we map each meaningful unit correctly before encoding them into quantum states. After tokenization, we convert the sentence into a string diagram. For this we use the parsed parser, a very powerful parser based on combinatorial categorial grammar. With parser.sentence to diagram, we feed the tokens and get a complete string diagram representing both syntax and the underlying quantum process. For our sentence, the cat sat on the mat, the string diagram shows how words like the and cat entangle using the cup notation, and you see types like n, n.l, n.r, and s representing the pre-group grammar. Now comes the challenge. The raw diagram may require 13 wires, meaning 13 qubits. This is expensive. So, we apply rewrite rules like the prepositional rule and determiner rule to simplify the structure. These rules reduce unnecessary wires, remove redundant grammatical structure, and give us a more compact version of the diagram. After rewriting, we use the normal underscore form function. This step is crucial because it reduces wire count, straightens bent structures, and gives us a canonical diagram. Two different sentences with the same grammatical meaning will collapse to an equivalent form, making it ideal for quantum processing. From this optimized diagram, we use the IQPNSATs to convert the diagram into a quantum circuit. We define our atomic types, assign qubits, for example, 1 qubit per noun, 1 per sentence, and then feed the diagram to the ansats. Instantly, we get a quantum circuit containing Hadamard gates, rotational gates, and symbolic parameters. These parameters are your trainable weights. Using circuit.FRE_ symbols, we can identify them and then initialize them with random values between 0 and 2 pi using np.random.uniform. This gives us a numerical parameter vector ready for optimization. Finally, once we have parameterized circuits, for example, for 2 sentences, we can run them, obtain classical outputs, and compare them using cosine similarity to measure sentence similarity or use them in classification tasks. Now, you might be wondering, what if we want probabilistic output from our quantum circuits? For that, we need a quantum backend. In this demonstration, we can use the AIR backend. Using the pytket package, we simply import AIR backend, compile our pytket circuit, and run it. Since we are working in the NISQ era, probabilistic results require multiple runs, called shots. Each shot samples the output state of the circuit, and after many shots we get a distribution over bit strings. Since our example circuit uses 7 qubits, the output will be patterns of zeros and 1s each representing a basis state along with its frequency of occurrence. With matplotlib, we can easily plot this as a histogram. The quantum measurement gives us a probabilistic representation of our sentence. Of course, these patterns don't yet give deep insights because our parameters are randomly initialized, we haven't trained anything yet. But they show how quantum circuits encode sentence meaning as measurable quantum states. Now let's move on to something more interesting, classification. Suppose you want to classify sentences. We start by building a dictionary of sentences along with their labels. For each sentence, we generate the string diagram using lambeq, convert it to a quantum circuit using the ansats, and then feed these circuits into a machine learning pipeline. To train the model, we define a loss function. For binary tasks, we can use binary cross-entropy, and alongside it we can track metrics like accuracy. Then we use the quantum trainer to optimize our model. We pass the model, loss function, optimizer, training epochs, and hyperparameters. Here, we are using the SPSA optimizer, which is widely used in quantum machine learning because it works well even with noisy circuits. During training, we provide the trainer with training and validation datasets, specify evaluation metrics, and even set early stopping criteria so the trainer halts automatically when performance stabilizes. After enough iterations, the model converges and learns optimal parameter values. We can also visualize the loss and accuracy graphs to observe how the model improves over time. So today, we explored how category theory helps transform sentences into structured diagrams, how those diagrams become quantum circuits, and finally, how these circuits can be trained for real-world NLP tasks like classification. This is the future of language processing, where quantum mechanics and linguistics come together to unlock deeper understanding. Thank you so much for watching and learning with me today. I hope this session helped you understand how category theory, string diagrams, and quantum circuits come together to form the foundation of quantum natural language processing. If you found this interesting, don't forget to like, share, and subscribe, and stay tuned for more deep dive sessions on quantum AI, NLP, and advanced machine learning. Thank you once again, and see you in the next video.